In this video, we will discuss eigenvalues and eigenvectors. These are incredibly important to understanding how to solve differential equations. This video will recall some of the basic definitions from linear algebra, and then we will go over some examples on how these ideas are used in this class. We begin with the definition of an eigenvalue. Given a linear operator L on a vector space V, a scalar lambda is called an eigenvalue of L if there exists a non-zero vector x such that L acting on x is equal to lambda times x. The vector x is called an eigenvector associated with the eigenvalue lambda. The idea behind eigenvalues and vectors is that there's a vector such that when L is applied to it, the vector doesn't really change, except possibly to get scaled, become longer or shorter. For an example, let's consider this matrix. We can easily verify that this matrix has an eigenvalue 3 associated with an eigenvector 1, 1, and also an eigenvalue negative 1 associated with the eigenvector 1, negative 1. When you consider the eigenvalue and eigenvector together, we call them an eigenpair. Being able to find eigenvalues of a matrix is not going to come up very often in this class, so I won't go into the details of the computation for how I found the eigenpairs for this matrix. For another example, let's consider the differential operator defined by the derivative. This operator acts on the space C1, AB, and outputs the derivative of the input vector. For operators acting on a function space, we often call the eigenvectors eigenfunctions, since the vector is a function. So we are looking for a function such that when we take its derivative, we get basically the same function back, except for a constant out in front. So pause the video for a second, take a minute, try and think of a function that has that property. Alright, so one such function is the natural exponential function, e to the x. This, in fact, will give us e to the x back after differentiation, so the eigenvalue is just 1 in this case. But in general, we can actually find infinitely many eigenpairs for this linear operator by considering the function e raised to the lambda x. When we differentiate, the lambda comes down in front via the chain rule, and we get that L times e to the lambda x is equal to lambda times e to the lambda x. So we get an infinite number of eigenpairs, lambda e to the lambda x. This is an interesting difference from matrices, where whenever you found the eigenvalues of a matrix, you only got finitely many of them. Now we can have infinitely many eigenpairs. Recall that the transpose of a matrix takes the ij component of the matrix and changes it with the ji component. As an example, let's consider the matrix 1, 6, 4, negative 2. The transpose of this matrix is given by flipping the off-diagonal elements, giving us 1, 4, 6, negative 2. While it is generally easy to find the transpose of a matrix, we will be considering linear operators that use derivatives in this class, so we need to find a different way of discussing the transpose. It turns out the transpose can also be defined by using the inner product. Given a matrix A, the transpose of that matrix is going to satisfy the following equation, called the bilinear identity, for any vectors u and v. So the inner product of AU with V will be equal to U inner product with the transpose of A acting on V. So this transpose operator, AT, will satisfy this entire bilinear identity. Remember that A acting on U and A transpose acting on V are both vectors, so really what we're doing here is just an equation considering the inner product of two vectors. A matrix is called symmetric if it's equal to its transpose. Using our inner product definition of transpose, this means that a matrix is symmetric if it satisfies the given equation, A acting on U inner product with V, is equal to U inner product with AB for all vectors U and V. So essentially the same as the identity given above, except instead of having an A transpose, we replace it with A. There are three very important theorems regarding symmetric matrices and eigenvalues and eigenvectors. While these theorems are stated in terms of matrices, we will see that they apply to other linear operators as well, in particular operators that involve functions and derivatives. The first theorem says that all eigenvalues of a symmetric matrix will be real, and also that the eigenvectors will be real. The second theorem states that for a symmetric matrix, if we consider two eigenvectors that correspond to two different eigenvalues, then the eigenvectors, x1 and x2, will be orthogonal. Finally, we get the big one, the spectral theorem for symmetric matrices. This is really just an extension of the second theorem, and it says that for a symmetric matrix that is n by m, then the eigenvectors of that matrix will form an orthonormal basis for Rn. This makes finding the eigenvectors of a symmetric matrix very useful, as it will give us a nice, useful basis for Rn for which to use. As I said, we will not be doing a lot of work with matrices in this class, but this spectral theorem for symmetric matrices, it extends very nicely to differential operators, and it will allow us to find a basis for complex function spaces such as C1AB.